Hello, everyone. Thank you so much for being here. We're going to start the Q&A in just a few minutes, a little bit less than 5 minutes. So just wanted to welcome you if you're new here or new to my channel overall. Thank you. I'm so happy that you guys are here. Pretty much just want to explain how this Q&A works. And once we start at 12 o'clock, so like I said, in a little bit less than 5 minutes, you can go ahead and place your question in that chat box. And if you have a specific question with like an actual example with numbers or a balanced equation, whatever you're asking, that makes it so much easier for me to answer as many questions as possible in this hour. So I'd say if you have a chance, look up those questions, and that's what you should be placing in the chat box. I go in order of people who are pretty much, it's first come, first serve. Think of it that way. So whoever, asks a question, I'm putting it all in order and answering in order. So of course, if I do have several people of like the same person asking, let's say like 10 questions, I will at least pick one question from each person. Okay. So as everyone starts to kind of come in, as mentioned, if you guys have a specific question that is awesome, that's really, really helpful, rather than just the topic. So, I can still make do with that, but just know that it's a lot easier to answer your question if you have a specific one. Okay, so we still have about 3 minutes. I also wanted to talk about just the other things that I'm doing with this channel and trying to just do my best to help you guys out besides having videos and Q&As. I know that there's still questions. So to help you with those questions and just to help you really pass chemistry and excel in chemistry, I've been creating really, really detailed notes that go in an order. They're designed in a specific order to help you understand the concept and to see all the different possible ways to actually see a question. So it prepares you for several different types of, ways a professor or teacher can word a question and make sure that you get it right on your exam. So I will be placing, that's actually already in the description box of this video and of every single one of my videos. You can find my notes there. Right now I have molarity, and molarity includes solution stoichiometry, titration, dilution. So if you're having a problem with that, definitely check that out. I also have limiting reactants, anything to do with limiting reactants, excess reactants, theoretical yield, all the yield, percent yield. There's multiple examples there that are literally step by step. I'm explaining every single step and why. So that is extremely helpful. I definitely recommend checking that out. I also have Lewis structures, and I'm currently working on redox reactions. That should be out this week. So as I mentioned, awesome. People are starting to put their specific questions. Thank you. That's really helpful. So I also have, if you are new to my channel or just aren't familiar with the other things that I do, I welcome you to join the community. What this is you can fill out a form, and my gift to you is a formula sheet. So it's a formula sheet with all the different formulas that you're going to need this semester for Chemistry 1. I'm still working on the second half of chemistry, but that is my gift to you. It makes it so much easier so you don't have to, worry about searching through your book, searching through your notes to find that formula, that one formula. Instead, it's all grouped together in just one document. So definitely recommend that. As everyone starts to kind of come in, this is just awesome. I love seeing that everyone is, coming in, having different questions, and getting ready to answer them in less than a minute. So as mentioned, if you guys are starting to just come in right now, definitely check out those notes that I was talking about. Extremely helpful. I'm working on them every single week to provide you with new notes and new topics. And then I'm also still working on videos to launch this coming week. And I just got someone saying my chemistry teacher showed me one of your videos and they are extremely helpful. Thank you. You're welcome. Wow, that's awesome. It's really cool that teachers are actually showing my videos overall. Wow. Okay. Evelyn says, love you, Melissa. Thank you for helping me with chem. Oh, much love to you as well, guys. I'm so happy to help you guys out with chem. All right, I'm ready. So I'm ready to start. Let's go ahead and start off with the first question. All right, and we have a specific question on stoichiometry. So calculate the mass of silver bromide produced from 22, let me write everything down, 22.5 grams of silver bromide. Well, actually, that was nitrate. So we have silver nitrate. Okay, so we have silver nitrate in the following reaction. Let me place the balanced equation here. So awesome. They provide you with the balanced equation. And as I start writing this all out, guys, just everyone who's starting to come in right now, as mentioned, if you have a specific question with numbers, with balanced equations, that helps me out a lot just so I can really make sure to answer your question. Okay. Let's see what we got. So far, this is all that we're given. We're given 22.5 grams of silver nitrate, and so this was our given. We're asked to find the mass, so really grams of silver bromide. Okay, so we're going from grams of silver nitrate to grams of silver bromide. Let's build a plan. So building our plan, we're going to start off with grams of silver nitrate because that's what we're given with. We always start with what we're given. And then we're going to get down to moles. So if you're not sure where to start, everything really equals moles. So that is like the best way that I can tell you. If you're not sure where to start, change that to moles. So that's what I'm going to do here. I'm going to change this to moles of silver nitrate. Now we're asked to find a completely different compound, so we have to change the compound now. How we do that is by using a mole-to-mole ratio from our balanced equation. So I'm now going to change this to moles of silver bromide. And then lastly, using the molar mass of silver bromide, I'm going to change that to grams. Okay. So let's start off with just finding the molar mass because I will need that for that first conversion factor. From going from grams to moles, we use molar mass. So let's find the molar mass of silver nitrate. And then what I'm going to do is just separate every single element apart and write its individual mass. So let's go back to our periodic table, which I'm going to grab mine. So silver is 107.87 grams per mole. And then nitrogen is 14.01. Oxygen is 16. However, there are 3 of them, so I have to multiply that by 3. Once we do that multiplication, that'll be 48. Then I'm going to add all of these numbers up, and that will give me my molar mass. So let's add everything together. So 107.87 plus 14.01 plus 48. That'll be 169.88 grams per mole. And I'm going to start setting this up. So starting with the 22.5 grams of silver nitrate, I'm going to align the grams of silver nitrate across from each other. So placing that on the bottom so it can cancel. And then I'll put the molar mass on the bottom. So remember these grams or this, 169.88 is going to go with the grams. And this is always going to be for every 1 mole of silver nitrate in this case. Okay, now that I have my grams and grams canceling, we're at moles of silver nitrate. So now we have to change the compound. So now let's go back to that plan. And we're here at step 2, where we're going from moles of silver nitrate to moles of silver bromide. And I'm going to go back to that balanced equation because this is going to be very important for a mole-to-mole ratio. I'm going to take the numbers in front, or the coefficients in front of that compound, and use those as my mole-to-mole ratio. So here we have 2 moles of silver nitrate per every 2 moles of silver bromide. So that's exactly what I'm going to set up here. So let's go back to the second half, aligning the units again so they can cancel. So placing the moles of silver nitrate on the bottom, and then moles of silver bromide on the top because that's what we're looking for. We're looking for that compound of silver bromide. And then we found that it was a 2 and 2 mole-to-mole ratio from our balanced equation. And then lastly, I'm going to place the moles of silver bromide on the bottom. And then we're going to grams of silver bromide. So once again, I need to find the molar mass. So let's find the molar mass of silver bromide. So silver we said was 107.87, and then bromide is 79.91. I'm going to add this together. Grab everything. There we go. Okay, 107.87 plus 79.91. This will give us 187.78. That's going to go on top with the grams. And then on the bottom, it's going to be per every 1 mole. Okay, so you'll note that your moles and moles will cancel of silver nitrate. Then we got to moles of silver bromide, and those would then cancel. And then finally, we're getting to what we're actually solving for, which is grams of silver bromide. Okay, now I'm going to multiply everything out. So what I'll do is multiplying that 22.5 times the 2 times the 187.78. Then I'll divide this by these two on the bottom multiplied out. So let's do that. Multiplying everything on top times 2 divided by 2 times 169.88. And then we'll get 24.87 grams of silver bromide. Now I'm going to make sure I'm rounding to the correct amount of sig figs. So I'm going to go back to our given. And our given was 3 sig figs, so I have to round to 3 sig figs. So my final answer will be rounded up to 24.9 grams of silver bromide. So the main thing with stoichiometry, as you're probably noticing here, is just understanding what steps to take. So you're always going to pretty much just convert this to moles first, and then make your way. If you have to change the compound, that's where you use a multiple ratio. If you ever see atoms or particles or something like that, molecules, you'll use Avogadro's number. So it's just knowing which conversion factor to use. Okay, so Juliana, that was your question. Hope that makes some more sense. And then Isabella states nomenclature. Okay, so let me go over some different types of nomenclature. Let's start off with so by the way, just real quick, remember that there's going to be 2 different types of compounds overall. So you're going to have ionic and you're going to have covalent. So that's the main thing with nomenclature, is understanding which compound is it automatically. So if it's ionic, it's going to consist of 1 metal, and that's going to be positively charged, and a nonmetal, which is negatively charged. Your covalent compound is going to consist of 2 nonmetals. Okay, so that being said, let's go ahead and figure out here. Let me make one up real quick. So I'm going to start off with an ionic compound. So an ionic compound, we stated, was a metal and a nonmetal. Okay, so let's say if I had calcium. Sure. If I had calcium and I had, I'm going to state that it's oxide. And then, by the way, the reason why I'm doing this, the reason why I'm doing oxide instead of just oxygen, the rules for naming ionic compounds is that we're always going to have the standard name of the metal. That's going to be consistent, okay? However, the nonmetal will always end in "ide." All right, so that is always the case when you're naming ionic compounds, or really just naming in general. Even with covalent compounds, your nonmetal will always end in "ide." And how I want you to think of it, it's the second one, okay? So here we have the first one, which is calcium, and then the second one, which would be oxide, would be the one that ends in "ide." All right, so then from here, with ionic compounds, we always have to balance out our charges. So charges are extremely important in this case, where calcium has a 2+ charge, and then oxygen has a 2- charge. You'll note that these are already balanced, so I can automatically just put them together. So there we have it, calcium oxide. If we were working our way backwards, so let's say if we had something like this, okay, and we're making our way backwards, we'll see that Mg, or magnesium, is a type of metal, so automatically it has to be ionic. So I'm just going to write the name of the metal. And then chlorine is a type of nonmetal, so that means it has to end in "ide." And that's all it would be, so it would just be chloride. Now, the reason why there was a 2 here initially, let's think back to what if I had to, go backwards. And instead, I didn't know the chemical formula. Instead, they just gave me the actual name. So magnesium, we would know it was Mg with a 2+ charge. And then chloride or chlorine has a -1 charge. And then you'll note that they're not balanced. So the charges are not balanced. So really, I just have to put a 2 to balance out that chlorine. So it would have been magnesium chloride with the 2 subscript. So that's the main thing with nomenclature. And a little trick for you, you're going to get into polyatomic ions. So they're always going to end in ate or ite, with the exception of a few that do end in ide. Hydroxide is one of them. So is cyanide. So hydroxide would be OH with a negative charge, and then cyanide would be CN with a negative charge. So those are just the rare ones. But in this case, polyatomic ions are always going to be ate and ite. So that's something to definitely check out. By the way, I do have a lot of videos on nomenclature, so I recommend checking that out. Real quick, I'll do an example of a covalent compound, and then I will move on. So covalent compound, let's say if we had nitrogen, and then tetra fluoride. Okay, so covalent compounds, remember, they consist of 2 nonmetals. So whenever we see these prefixes, that's going to tell you how many elements there are of that one. So the covalent one I feel is a lot simpler, just because you don't have to balance out the charges. It literally tells you how many of each element there are by that prefix in front. So di meaning 2, nitrogen just states, okay, there's 2 nitrogen. And then tetra, that means 4. So that tells us there are 4 fluorine. So in that case, that's it. That's all we're looking at. Okay, so first things first, identify what type of compound it is. Then you can go about the rules and understanding, all right, how am I going to name this? Let's see our next question. Evelyn states, can you go over some example problems with Planck's constant and speed of light formulas? For example, cool, he gave me an example, thank you. What is the wavelength? So I'm going to start here. So right off the bat, this is asking us to find wavelength, and this is just the symbol for wavelength. So we're solving for the wavelength, specifically in nanometers. That has a frequency. Okay, so we're given our frequency, and then this is our little symbol for frequency. So we have 6.6 times 10 to the 14th hertz. Okay, so we have to figure out what's the formula. That's going to be the main thing to focus on here. Okay, so let me go into, this is electromagnetic spectrum. You're going to have several different types of formulas. Let me write them all out and show you. Where is it? I believe it's, here it is. Okay. Let me write all the different formulas out that we can possibly see, and then definitely know those. However, I'll show you which one pertains to this exact example. So the first one, the first equation that you'll see, or formula, is that frequency is equal to the speed of light, or c, divided by our wavelength. The second one you'll see is energy is equal to Planck's constant times our frequency. And then the third one is putting them both together, where energy is equal to Planck's constant times the speed of light divided by the wavelength. Okay, so in this case, we're given our frequency, so we have to pick a formula that has frequency. So this third example, or this third formula, is out since it doesn't have frequency. Now we're asked to find wavelength, so really we have to find a formula that has both of these, has the wavelength and it has the frequency. So that's going to be just the top one. So that's going to be the main thing to look at, is which one, which formula am I using? So I'm just going to start off with the top one. And this would be that here, right there it is. So frequency would equal the speed of light divided by our wavelength. Okay, so I'm going to actually rewrite this formula, rearrange it, just so we're actually finding wavelength. So I can do that, and I'm going to multiply both sides by our wavelength. Then those would cancel, remove the fraction, and now Now what's left is that c, or the speed of light, is equal to our wavelength times our frequency, and I'm going to divide over our frequency to the opposite side, and then our wavelength now equals the speed of light divided by our frequency. Okay, that's the formula I'm going to be plugging everything into. However, we don't have the correct units at the moment, and how I knew that is by knowing the units of the speed of light. The speed of light is roughly 3.0 times 10 to the 8th meters per second, or divided by seconds. What we were given with our frequency was it's in hertz. So something that you have to know is that 1 second to the negative first power is equal to 1 hertz. So really, it's just 1 to 1, which is nice because we could automatically just change this to 6.6 times 10 to the 14th, and it's really just seconds to the negative first power because I'm just replacing this hertz to seconds. Okay, so that's really the unit that we're going to be using. Now, I'm just going to plug everything in. We have our speed of light, we have our frequency in the correct unit, which I'll put over here again. Plug everything in, solve, and almost there. So 3.0 times 10 to the 8th meters per second. This will be 6.6 times 10 to the 14th seconds to the negative first. By the way, what seconds to the negative first really means, it just means 1 over seconds. That's all. So here we'll see our seconds and our seconds will cancel. We'll divide these two values, and that'll give us our wavelength in meters. So we have one additional step to change it to nanometers at the end. So 3.0 divided by, actually, to the 10 to the 8th, there we go, divided by 6.6 times 10 to the 14th. Okay, it gives us our wavelength of 4.545, I'm going to round everything to the end, times 10 to the negative 7th, and that'll be meters. So I will change my sig figs real quick. Looking at this, we were provided with just 2 sig figs, so I will round just to 4.5 times 10 to the negative 7th meters. Finally, last step is to convert this to nanometers. So I'm going to put the meters on the bottom so they can cancel, and the nanometers on top since that's what we're looking for. There's one for every 1 nanometer, there's 10 to the negative 9th meters. And from there, I just have to solve. So once we do that, divide by 10 to the negative 9th, here we go. We'll get 454.54 nanometers. And that's essentially it. I will leave it. So the typical case here is this is what you typically want to see for nanometers. I know it's not technically the correct amount of sig figs. That's just typically what your wavelength looks like. So this is kind of like an exception. If your teacher really is that picky with sig figs, then what you can do is just change this to scientific notation again, where you move this over 1 to 4.5 times 10 to the second nanometers. Those both are the same. But like I said, we typically measure nanometers. Like it looks like that. It's 454 nanometers. So yeah, that's really it, Evelyn. Okay, let's move on to the next question. All right. So as of now, we are getting a bunch of questions. So right now what I'm going to do is answer at least one question from each person. And then, of course, if I have more time, I will come back to your guys' other questions. But I at least want to answer and be fair, to give everybody a shot to get their question answered. So next, I'm going to answer Starship's question. If you start let's start off with everything that we're given. We have 14.8 grams of C3H8 or propane, and 3.44 grams of O2. Determine the limiting reactant and the maximum yield of H2O. Okay, so we're going to find two different things. So we're finding I'm just going to say LR, that just means limiting reactant, and we're finding our yield of H2O. Okay, so max yield. Whenever they say maximum yield or minimum yield, they're just referring to the theoretical yield. The theoretical yield, once again, is whatever your limiting reactant produces. So the first step here is just to figure out what our limiting reactant is, and we're also going to build a balanced equation. So actually, our first step is going to be building a balanced equation since we're not provided with that. As you might see here, they tell us our reactants, okay? This is a combustion reaction, so it will always produce CO2 and water. Now, all I have to do is balance this out. So balancing this out, we have, let's just write everything out and see how many of each we have. So we have 3 carbon, 8 hydrogen, 2 oxygen. On the other side, there's 1, 2 hydrogen, and there's 2 and 3. Oxygen. Okay, so I'm going to start off with just balancing out the carbon and putting a 3 in front of here, distributing and seeing how that changed. So now we have 3 with our oxygen. This is 3 times 2, giving us 6, plus this extra 1, giving us 7. And we're still not balanced just yet. Let's balance out the hydrogen. I always leave oxygen to the end. So hydrogen, we have, let's put a 4 here to make it an 8. Distributing this, that'll be 4 times 2, which is 8. Nothing changed with our carbon, and let's recount our oxygen. So oxygen on this side had 3 times 2, so 6, plus 4, really just 4, giving us 10. So now we have 10. Now to balance out our oxygen on the reactant side, I'm just going to place a 5 here to give us 10, and we finally are balanced. Okay, so let me erase this chunk, and then let's see what else we got. Okay. Don't think it's going to let me. Okay. I'm going to move on to, here, let me rewrite this. This is going to be our balanced equation that we will have to use to pretty much do stoichiometry again. Okay. So what we have to do for our limiting reactants to just figure out our limiting reactant is go from grams of every single reactant. So I'll start off with our first reactant and get to grams of a product. Now, they are telling us which product they want us to find. They're asking for water. Since they're asking for the maximum yield, they mean go from grams of your reactant to grams of a specific product, which is water. Okay, now let's do this. Let's build a plan. So grams of propane, and we're going to change that to moles of propane. Then we'll convert that to moles of water since we're changing the compound. And then we'll get to grams of water. Okay, so starting off with our given information that we have 14.8 grams of propane. I have to figure out the molar mass of propane, so let's do that again. Carbon has a mass of 12.01. Multiply this by 3 since there's 3 of them, so that'll give us 36.03. And then hydrogen, that's really 1.01 times 8 since there's 8 of them, giving us 8.08. Okay, adding this all up, let's see what we get. We'll get 44.11. And I'm going to place, and that's grams per mole, I'm going to place that on the bottom so it can cancel with the grams of propane. So just using molar mass here to allow us to get to moles of propane. And then from here, I'm going to change this to moles of a different compound. So moles of water, since that's what we're looking for. And let me put that on top. Placing that on top. Moles of propane will go on the bottom since we want those to cancel, and moles of water will be placed on top. Where we're going to get this information is from our balanced equation that we just balanced. So let's go back to the coefficients in front. So we want to figure out how many moles of propane there are and how many moles of water we have. So since there's no coefficient there, I'm going to just state that it's a 1, and there are 4 moles of water. So, okay, let's place that here. So 1 and 4. And keep going. We canceled those moles of propane. Finally, let's get to grams of water. So placing the moles of water on the bottom, and molar mass again is what we're going to use. If we were to do the molar mass of water, this is H has really 1.01 times 2, which is 2.02. Oxygen is 16. Adding those together would give us 18.02. And this is a 1 on the bottom. Okay. So let's figure out how many how much this reactant is going to produce, and then we'll have to do the same exact thing for the other reactant. Let's multiply everything out. So I'm going to multiply the entire top portion out, so 14.8 times 4 times 18.02, and divide that by the bottom, which is 44.11. So we'll get 24.18 roughly grams of water. Now, this is telling us this is what our first reactant is capable of producing. Let's figure out what our other reactant is capable of producing. So the other reactant was O2. We were given 3.44 grams of O2. And then we're going to do the same exact thing, where we're going from grams of O2 to then moles of O2 and keep going, moles of what we're looking for, which is water. And then we'll get to grams of water. And then at the end of this, we're going to compare how many grams of water each one produced. Whichever produces the least is our limiting reactant. And then let's get to moles now using the molar mass of O2. So O2, this is really just going to be 16 times 2 or 32. Placing that on the bottom and 1 mole of O2 on top. Our grams and grams will cancel. Let's move on to our mole to mole ratio, which will go back to our balanced equation. So moles of O2, let's see what we got. So we have 5. So looking here, we have 5 moles of O2 for every 4 moles of water. Let me go back and place that. So we said 4 moles of water for every 5 moles of O2. And then now all we have to do is bring back that same molar mass that we found before for water, placing the moles on the bottom so the water moles can cancel. And then we'll place the same thing, 18.02, multiply everything out. So multiply everything on top out, we'll get 3.44 times 4 times 18.02. Divide this by 5 times 32. This will give us 1.54. Let me make sure I multiplied everything out right. We are starting with a very, very small number compared to our first part. 5 times 32. Yes, I did. Okay. Grams of water. All right, so this is what our O2 produces. So looking here and looking here, we're going to compare those two values. So which one produced the least amount of product would be O2. So this is our limiting reactant. What we then produce is going to be our maximum yield per se, just because that's our theoretical yield. What I want you to think of when they're telling you what's your maximum yield, what's the max you can produce, well, the maximum that you can produce is whatever your limiting reactant is capable of producing, because that's how, think of it as like ingredients, that's all you have accessible to you. So that's really it. This would be the max yield, and that's all you had to do. Okay, next question as I take a sip of water. Let's see. Okay. Abinea states, actually, let me clear this all out and make some room, and then I'll move on to the next question. Okay. So we have pH is 5. pH of 5 is 10 times more than pH of 4. I'm not sure how to solve that. Is 10 times more blank than pH of 4. I think it's just asking, here, let me see what it's asking. pH of 4 is 10 times more, I would think, concentration than pH of 4. Is that all it stated? I can tell you what I'm thinking. So what I'm thinking it would be, when we're looking at pH, the formula, by the way, and what we're really looking at is how acidic something is. So these two pHs are going to be acidic since they're below 7. Now, what I would assume it's stating is it would be 10 times more acid. So our hydronium ion, you might have seen it like this, or H+, they both mean the same thing. So I would state that it's more of our concentration of our acid, just because it does have, and actually, no, I'm sorry, opposite. pH of 4 has more acid. pH of 5 has more base. How I just thought of that, by the way, was because if we were to look at our pH scale, the higher the number, the more basic it is. And the lower the number, so here's 7, this is neutral. So like within this range, it's going to be basic. Once it's below 7, it's going to be more acidic. So if we had something that was 4 and 5, it's higher up, meaning it's going to have more base. That's what I would assume it's asking. So the answer I would state would be it has a higher concentration of our OH, which just makes it more basic. Yeah, because a pH of 4 is lower, it would have more acid. That's what I would state it's stating. Okay, I'm going to move on to someone else who hasn't asked a question yet. So Marshall asks, how much heat is produced when 75 grams of steam okay, so this is steam, and then 135 degrees Celsius, at 35 degrees Celsius is converted to ice. So we have it at ice, negative 40 degrees Celsius. And they're not giving me any constants, are they? All right. So you're looking at phase diagrams. Actually, I'm sorry. You're looking at heating curves. So let me go to all of my constants because I will need them. This is specifically for water. So you will have to know all your different boiling points, all your different melting points, as well as all your formulas. So let me grab all those just because those are very important. Okay. I believe I had that all at the back. There we go. All right. Might have to look. Marshall, did they give you any other, because this is steam, this is that. Did they give you any constants like for C, meaning the heat capacity, specific heat capacity? Did they give you any of that? If not, I'll look it up. Not too bad. Let's see. Here, I'm going to start off with this question and just show you what everything's going to be. So a lot of times what we're doing, so this is a little bit of a longer question, we're looking at heating curves here. So we're going to start off with something that's in its solid state. Then think of it as every single vertical line is going to state something in changing its state. And then anything that's in its horizontal line, that's just some sort of process. So this would be fusion, and then this would be vaporization. And I'm going to put all of the different formulas that we'll have to know to figure out how much heat is produced. All right, so for our solid, that's just going to be our, wrong thing. Here we go. That's better. Q equals MCAT formula, where we have our mass times our specific heat capacity and our change of temperature. So yeah, specific heat capacity is something that we're going to need. I'm going to look it up if you don't have it. If it doesn't provide it with the question, it should. And then our fusion formula would be Q is equal to N, or the moles, times the change of our enthalpy of our fusion. And then let's see what else. Our liquid here would be Q equals MCAT again. By the way, every single type, every single solid, liquid, and gas would be Q equals MCAT. That's not going to change. And then lastly, for vaporization, right here, I'm just putting all the formulas that you'll need. N times our change in enthalpy of vaporization. Okay, so you'll note that all of these are going to require constants, different constants. So that's why I'm asking if you have that already. If not, I'll look it up. Okay. So I'm going to build on what it's giving us here. They don't give you it. Okay. That's shocking. I'll look it up. No problem. Okay. So we have solid, liquid, and gas, and we are asked to start off from ice, or actually we're going to convert it to ice. We're going backwards. Okay. So we're going from steam, which is right here, and they're giving us a specific temperature. So I'm going to place that 135 degrees Celsius at the top. And then at the bottom, we're getting to ice. So we're going this direction. to get to ice. When we're going backwards, meaning we weren't going in the endothermic direction, we weren't going, really straight this way, that would be positive. However, if we're going back down the opposite way, that makes all of these negative, okay? So all of these formulas will be negative because we're going the opposite direction, the exothermic direction. So negative, all of these will be equal to a negative here. I'll put a negative, negative. So all of those formulas, we will need all of these, and at the end, we're going to add everything together. Okay, so we have our steam. We also were given a final temperature, which was negative 40 degrees Celsius at the bottom. What is important to know is your melting point and your boiling point for water. So your melting point for water would be 0 degrees Celsius. Your boiling is 100 degrees Celsius. That is very important to know because this is going to tell you where to pretty much put everything, and we will have different changes in temperature. So I'm going to place the 100 degrees Celsius there, the 0 degrees Celsius and the 100 degrees Celsius right here. So now that I'm building all this, now I have to figure out what formula to start with. So we're going to start off where they first gave us, so with steam. Then from there, we're going to get to vaporization. Then we'll get to the liquid. Then we'll get to fusion. And lastly, we'll get back down to just it being a solid or ice. So there are 5 steps to this. Okay, let's start off with the first one. So the first one is still going to be gas or steam, where this is Q is equal to negative, since we're going in the opposite direction, mass times our specific heat capacity of steam. And you know what, let me look that up real quick as I do so. Specific heat capacity of water. And there's going to be different types. Let me put steam. Okay, come on. Hoping it gives it to me in the units that I'm looking for. Let's see if I can find it. If not, I might just show you the steps and go from there. Actually, I found it. Perfect. Okay. So here it is. What they should have provided you with was that the heat capacity of water would be 2.03 joules per grams Celsius. Okay, there we go. So this is for specifically steam. I'm going to plug everything in and solve. So we were given a mass of 75 grams, and then our specific heat capacity, plug that in as well. The main thing with these, I would say that is a little bit tricky, is figuring out your change in temperature. Remember, that's your final minus your initial. So let's go back to the diagram that I drew. So here, the reason why I put, the boiling point and the melting point is because we're not just subtracting the, final, like the steam to the ice, we're subtracting from every little change in state. So we're going to subtract really 100 minus 135, because this is our initial. We're starting off at 135. We're going to our final temperature of 100 degrees Celsius. So that's what my first change would be, 100 minus 135. Okay, so let's put that here. So 100 minus 135, that will give us a negative 35 degrees Celsius. Then we'll multiply all this out and see what we get. So those just come on down. All right, let's see what we get. So 75 times 2.03, our negatives would cancel, and we'll get 5,328.75. This would be in joules, because your grams and grams would cancel, so would your Celsius. And then since it is heat, it's just going to be joules. Okay, that was just for the steam. Let's go back now to the second part of this, which is going to be our vaporization. We're going to be using this formula for part 2. Okay, so then now I need to figure out, luckily, cool, what I found gave it to me. Awesome. Okay, so I'm going to use this other formula this is for vaporization. And then this is going to be negative our moles, so we have to figure out our moles, and then our change of enthalpy of vaporization, and that's it. So let's start off with just figuring out our moles of water. So this is 75 grams of water. Our molar mass of water is 18.02 grams of H2O per every 1 mole. I'm just converting this to moles, and I'll divide and see what that gives us. So N will now be equal to 75 divided by 18.02. So 4.16 roughly. And then that's what I'm going to place here. Oh, by the way, so they should have given you this also. This is going to be a vaporization. So this is 40.6 kilojoules per mole. Okay. So plugging everything together, this is in moles, and then this is in kilojoules per mole. The moles and moles will cancel. So moles and moles will cancel. Multiply these two together, and we will get negative 168.97 kilojoules. Because our previous answer was in joules, I'm going to automatically change this to joules. And this would give us, did it tell us in kilojoules? No. Okay. So I'm going to change this to joules, dividing this really by 1,000. Okay. And actually, opposite. There are 10 to the third or 1,000 joules per every 1 kilojoule. There we go. Okay, so multiplying this out, this would give us negative a very large number, joules. We have to do this again. So as you can tell, this process is very long. Now I'm going to move on to the third, if I can come back to this. So we're at our liquid phase. So looking at our liquid phase, this is going to be Q is equal to MCAT again. However, our change in temperature is going to be final minus initial. So now that we've gotten down to a gas or liquid really, we're at 100 degrees Celsius. That's our initial. Our final is now 0. So we're going to subtract 0 minus 100. So that's going to be what we use for our change in temperature. Okay. So let's go back. This is going to be Q is equal to negative MCAT. And then negative 75 is what I'll place here in grams. Our specific heat capacity of water, because we're at a liquid now, is 4.18. I'll place that there. This is going to be joules per moles Celsius. And then we stated that the change in temperature would be 0 minus 100. So really it would have been a negative 100 degrees Celsius. Multiply everything out. So 4.18 times 100 times 75. That would be another large number in joules. And our negatives and negatives would cancel. Okay, almost there. So 2 more steps left. So for 4, we're going to use our moles again that we found previously, which remember our moles was 4.16. We're now at the step of fusion. So Q is equal to N times the change of our enthalpy of fusion, which that is 6.02 kilojoules per mole. And I'm going to plug everything in. So remember, this was our moles. Oh, by the way, this still is negative because we're going in the opposite direction. So this is going to be negative 4.16 moles times 6.02 kilojoules per mole. All right, so 4.16 times 6.02 would give us negative 25.04 kilojoules. Let's change this to joules. So 10 to the third on top, and then 1 kilojoule on the bottom. So really we're just multiplying this by 1,000, and that would be this other large number, and let's keep going. We got 1 more step to go. Actually, technically 2. Then lastly, we're finally at the solid state. So I'm going to go back to that little table that I drew again, but we will be using this formula. Let's figure out what our change in temperature is again. Okay, so our change in temperature, we're finally at this part. Yay. So here our initial is going to be 100 degrees Celsius and our final would be negative 40. Really what we're going to do is do negative 40 final minus initial. So we'll have negative 40 degrees Celsius for our final, for our change in temperature. Okay, let's go back. And then at the very end, we add it all up. So Q is equal to negative 75 grams. Our specific heat capacity of a solid would be 2.06 joules per grams Celsius. almost done with this question. And then this is going to be times our change in temperature, which we just said was negative 40 degrees Celsius. Multiply everything out. So 40 times 2.06 times 75. This would give us 6,180 joules, since our grams would cancel, so would the Celsius. And that would be positive since these negatives also cancel. Our last step here is to add all of our heat up. So all the Q's together. So I'm going to add up 6,180 plus everything else that we found prior. And here, let me go ahead and go back. So I'm going to start adding this all up, and then that would be our final answer. So plus a negative to 5043.2. And I'm just going to scroll back since we do have a lot of these. Plus 31350 plus a negative 168978.9. And I believe there's one more. How was that one? Plus, okay, almost done, promise, guys. 5328.75. Whew. All right, this question. As you can tell, it's a very long question, but it's really important to go in those steps. Our final answer would be negative 151163 joules. There we go. There you go, Marshall. Okay, so I know it's a long step. And let me move on to Andy's question. So let me clear all this, make some room. Okay. And then at any point, guys, just to let you know, I will be placing all of these questions. I'm already putting them in the description box, so you can go back to it at the end of the day today. I'll place the timestamps. So if you need to rewatch this, of course, to see that question again. Okay, so let's get to Andy's question. We're asked what volume, so we're finding the volume, probably in liters, of fluorine gas of F2 is needed to prepare, and let me write all of our givens. So we have 500 milliliters of chlorine gas at STP, and then we're given our balanced formula. Okay, so this is a little bit of gas stoichiometry. Perfect. Thank you for even providing me with the topic. All right. So the formula that was given, 2KCl plus F2 gives us 2KF plus Cl2, and it's nicely balanced for us. Okay. So let's see. We're asked to find the volume, so the liters of fluorine gas. I'm going to start off with just what they provided me with. So they provided me with 500 milliliters at STP. A lot of times, oh, by the way, what STP even stands for, there's specific values where pressure is equal to 1 atmosphere, temperature is equal to 273 Kelvin, and volume typically is going to be 22.4 liters per every 1 mole, if not stated. Now, let's start off with the 500 that we know that we have 500 milliliters of chlorine gas. Now, automatically, I'm going to change that to liters because what we're actually going to use, we have to figure out what our moles are. Okay, that's going to be our main thing here. So the fact that this is an STP, I would use the ideal gas law to figure out how many moles we have overall. So let me see if that, we could also use, we could actually get to moles a different way, come to think of it. Yeah, actually, we don't even have to do that. What we could do is just use this 22.4 liters per every 1 mole. So that's all I got to do. I'm going to move this milliliters to liters and then change that to moles. That'll give me moles of Cl2. And then from there, since we're asked to find the volume, really, after that, I'm going to do a mole to mole ratio and get to F2. And then lastly, get to liters of F2, once again using this conversion factor of 22.4 liters is equal to 1 mole. So when they're saying STP, this is essentially what they're talking about. They're just saying, you know, the main thing to focus on is that this amount of liters is equal to 1 mole. So let's start off with the 500 milliliters and change that to liters. We'll use the metric system where we know 1 milliliter is for every 10 to the negative third, or opposite, 1 liter is equal to 1,000 milliliters. And then from there, as we cancel those milliliters and milliliters out of chlorine gas, then I'm going to get to moles. I'll put 22.4 liters on the bottom per every 1 mole. My liters and liters will cancel. We're now at 1 mole of Cl2. And then we're going to use a mole-to-mole ratio. So that's why they provided us with the balanced equation. And we're going to get to the compound that we're actually looking for, which is fluorine gas. So let's go back to our balanced equation. And we're asked to find, or we're looking for, there's only 1 mole of F2, and there's really only 1 mole of Cl2. So it's a 1-to-1 relationship. So 1-to-1. And then from there, I have to convert this back to liters. So I'll use that 22 again. So 22.4 liters on top per every 1 mole of F2. And then that'll be it. So let's multiply this out. So 500 really divided by 1,000, or times 10 to the negative third. And then times 22.4 divided by 22.4, those really cancel. This would just give us 0.5 liters of F2. That's it. That's all you would do for that question. The main thing whenever there's talking about STP is just really knowing this conversion factor. All right. So Nella states, let me grab some more water again, and then here. Whew, we're just getting through these questions. Love it. Let's see what we got next. Okay. Butane is burned in oxygen and produces carbon dioxide and water, right? A balanced equation. And then from there, how many grams of water are formed when 5.0 grams of butane are burned. Okay. Let's start off with just our balanced equation. This is a combustion reaction. We're given butane, and then with any type of combustion reaction, you're always gonna use, and actually that looks interesting with butane being that formula. Here, we'll check that in a second, but you're always gonna have O2 being your reactant, and CO2 and water will be produced. So for butane, and let me double check that. I believe that should be more, but I just want to specify. Yeah, that's what I thought. So butane is in that formula. It's C4H4. Don't worry about how I knew that. that comes later on in organic chemistry. There's a formula for it, but that's what it should have been for butane. Okay. So now with this one, I just have to balance everything out right now. I placed everything in the correct location. So let's balance and see how many of each we have. Okay. So with carbon, there are 4, and hydrogen on the reactant side, there's 10, oxygen, there's 2, and carbon on the product side, there's 1, hydrogen, there's 2, oxygen, there's 3. So let's balance out our carbon first by placing a 4 right here. Then I'll distribute these 2, and what's going to change is this 4 will multiply with this 2, so giving us 8 oxygen plus this additional 1. So that would give us 9. Next, we have our hydrogen to balance out. So there's 10 on this side, 2 on this side. So I'll place a 5 here and once again distribute. So 5 times 2 gives us 10. And then let's recount those oxygen. So we said that there were 8 here. Plus, this is 5 really distributing to the oxygen, so 5 of them. So 8 plus 5 would give us 13. And we're still not balanced. Okay, so this one is actually going to give us a fraction. How I knew that is because let's look at our oxygen. There's a 2 here and there's a 13 here. There's no way that we can multiply a number by 2 to get 13. So instead what we're going to do is we're literally going to place a fraction here that is 13 divided by 2, or 13 halves. When we do this, Then the last step is to just multiply by 2 to every single coefficient to cancel out that denominator. So what I'm going to do is just multiply everything by 2. So let me erase a little bit of this just so it doesn't look so cluttered. And I'll rewrite it again. Okay, so what we're going to do is just distribute that 2 to every single coefficient. This 2 and this 2 would cancel, by the way. That's the whole point of this. So this is just finding our balanced equation. Our balanced equation would be 2 C4H10 plus 13O2 gives us 8 CO2 plus 10 H2O. That would be our first balanced chemical equation. And then they're asking for a little bit of stoichiometry here. So how many grams? So we're asked to find grams of H2O. And then we're formed when we're given. So we're given 5.0 grams of butane. All right, so our plan is going to be going from our grams of butane to grams of water. And how we're going to do this is, once again, we'll go from grams of butane. Then we're going to change this to moles of butane. And then we'll convert this to moles of water. And lastly, we'll get to grams of water. Okay, so we've seen this a lot with everyone's question. So I'm going to start off with grams of butane. So 5.0 grams of butane. And then change this to moles by using the molar mass of butane. So carbon has a mass of 12.01, multiply that by 4. Hydrogen has a mass of 1.01, multiply that by 10. So this would give us 48.04, and the bottom would be 10.01, 10.010. And then we'll add those two together, and this would be 58.14 grams per mole. So I'll place the grams of butane on the bottom. It was just that molar mass that we just found. And then from there, placing a 1 mole of butane. Next, our grams and grams of butane would cancel. We're at moles of butane. So now we're trying to get to moles of water. So moles of butane, and on top is moles of water. I'm going to go back to the balanced equation. Real quick, for the question you're doing, couldn't you make the O2 2.5, or should we times everything by 2? Always times everything by 2. With these, we typically don't make them into decimals. You'll see it as a fraction instead, and we want to keep it as a whole number. That's why we're multiplying by 2. Yeah. And then next, I'm going to go back to my balanced equation. So for that mole to mole ratio, okay. So actually, we were going from butane to water, and let me grab those coefficients in front. So we have 2 moles of butane per every 10 moles of water. So 10 moles on top per every 2 moles of butane. And lastly, I'll change this to grams of water. So grams of H2O per 1 mole of H2O. We'll find the molar mass of H2O. So H is 1.01 times 2, which gives us 2.02. Oxygen is 16. Add these two together, which gives us 18.02. Multiply it all out. So 5 times 10 times 18.02 divided by 2 times that 58.14. In total, we would get 7.74 grams of water. Let's make sure we're rounding to the correct amount of sig figs. So our initial given was just 2 sig figs with that 5.0. So I'm just going to round to 7.7 grams of water. That would be our final answer. Okay. So that would be it for today, guys. Answered as many questions as possible that I could in an hour. I'm going to be doing this again next Sunday, and the Sundays to come. So I definitely recommend being on time to really make sure to get, your questions answered. I do go in order, first come, first serve, and I'm just trying to answer as many questions as possible in this hour. Also wanted to mention, if you're new to these Q&As, if you're new to this channel, welcome, thank you for being here, and pretty much just want to kind of update you on what's going on, what I have for you guys, and you can see in the description box of this video and really all of my videos to join my community. And what that really is I give you guys an awesome gift. It's a formula sheet. So if you haven't signed up just yet, make sure to do so. You get a formula sheet with all the different formulas that you'll need to know this semester for chemistry. I personally wish I had that when I was taking chemistry, because you don't have to keep searching through your book or through your notes, and it's just helpful to know what everything is. Like I said, the link is in the description box. And also, I have my own notes that I'm making for you guys. They're very, very detailed. They go in a specific order that is designed for you, to learn and understand. I've been tutoring for over 10 years now, so I know the order that you guys will succeed when it comes to learning. I personally have done this myself. So I figured that order out when I was in school. So everything that I do in my notes, I do for a reason, even, color coordinating and, explaining things in more, in like English rather than chemistrarian. So I've seen that it's just really complicated how the book is always worded everything, right? Even professors tend to speak a different language, it seems. So I like to make my notes and really everything in English and in a really easy way to understand it. It's a really simplified way. So you can get those notes, definitely help support this channel. And I'm going to keep making notes for you guys. You can find that. I'm also going to keep making more videos for you guys, of course. So I'll keep making notes every single week. What I have so far for the notes, I have molarity and solution stoichiometry. Those are mixed together in the same notes. And that also has dilutions in it. So if you have any questions with those, definitely check it out. I recommend that. I also have limiting reactants. If you saw in my latest video, I have limiting reactants, and I talk a little bit about the notes there, where I also have excess reactants examples, theoretical yield, percent yield, actual yield. I do very, very detailed examples explaining not only how to do the problem, but why we're doing what we're doing. And that really helps you guys understand and pretty much prepare you for any single question or anything that you can be asked on your exam. That's what I'm trying to do, and that's what I'm here for. All right. So thank you everybody for being here. I really appreciate you guys, coming out and just being at this Q&A. I will be doing this again next Sunday at the same exact time. So 12 o'clock is here in California. This is Pacific time. So whatever time that, is for you guys, that's the same time I'll be doing. I hope to see you guys next Sunday. All right. Have a great day. See you guys.